Hiya. So in this video, we're going to continue our conversation on multiplication moments. And we're going to use this function idea in order to kind of help us determine what happens why the linearity condition for expected value is true. So the linearity condition, if you don't remember, which has been forever, is this condition here. So remember this we called the linearity of expected value, right? And so let's kind of see where this kind of comes from. So what we're going to do is we're going to make a function. So we make the function f of x, y, to be equal to x plus y, which is kind of what we want to solve, right? This is really where we're wanting to go, right? This is where we're wanting to go. And so by the above information, what we end up having is that that the expected value of f of x, or x plus y, this is just expected value of x and y, right? So let's look at this in a summation formula. So this is obviously going to look over every x and y, and we'll have x and y here. And because we can just pass things through, we don't have to worry about things. We just get x is equal to x and y is equal to y. And so what this does is it basically allows us to split things apart. So if I do L of x, y, so we have x plus y, p of x is equal to x, y is equal to y. This is equal to, because it should be enough room actually. So this, I can just sum over all x p of x equal to x, y is equal to y. Notice how in this case, this part just goes away by the law of total probability, so we don't really need to look at this. This is basically invisible. And then on the right hand side, we do all y p of x equals x, y equal y. And again, since we're summing over everything, this x equal x kind of disappears. And so we end up getting expected value of x plus the expected value of y. This is just a little proof of why this happens. I don't expect you to memorize it, but it's kind of a nice thing to note. Another thing that's kind of nice is that we can actually, so if we ever multiply by some constant, so if c is a constant, so c is a real number, then we can just pull that constant out. And this is not too difficult to see. So this, remember, we just take the function and we put it in front. And then we multiply by what's the normal probability. This c we can pull out, right? All x. And then this part is just the expected value. So that's kind of nice. So what this basically kind of says is if I have different things, right, like I have ax plus b, this is just aex plus b. So yeah. So this is like a kind of big thing. It's kind of nice. It allows us to break things up. So it's a fun little thing. Okay, so we're able to add. What happens when we try to multiply? And this is where we kind of run into problems. So if I were to try to multiply, right? So if I have a of x, y, and I try to do what we would do normally, right? Just as we did above, well, I can just do this x, y here. But notice here, I can't really split the x and y, right? Like I'm kind of stuck together. I can't, that's it. They're kind of stuck together. And so the point here is we're stuck here except in a certain case. If our variables are independent, so if we have independence, then we can actually split apart, right? This part becomes all xy, x, y, and then we can multiply. Remember how this is just and, the comma is and. So I can now split these apart. So if independent, we can split these apart. And then at this point, this is just distribution. It's just a normal distribution. Distribution not from the probability sense. Distribution as in like the distributive property. So just note that. And so what this gives us is this property. We have p of x equal to x times y, p of y equal to y. So this is distribution, not the probability version. And so here we can just multiply them together. So if they're independent, so the key point is if x and y are independent, then we can separate them. Or else we can't assume that we can multiply them out. So this only works if they're independent. So we're going to stop this video here. And in the next video, we're going to look at the second moment a little more and kind of see how that affects the probability distribution and stuff like that. So I will see you in that video.